Alright, so continuing with the linear mixed models lecture, I'm going to now talk about how to check model assumptions and how to compare models to decide which model to use for your data analysis. This turns out to be a slightly complicated story, but I will walk you through this, and finally I will show you how the likelihood ratio test that we learned several lectures ago, how that test is deployed in the linear mixed model for doing hypothesis testing, right? But that will be the only way that we will actually do hypothesis testing in the linear mixed model using the likelihood ratio test. And as I mentioned earlier, this is technically this is equivalent to the ANOVA, the analysis of variance, and so that's why in the linear mixed model the likelihood ratio test is implemented using the ANOVA function. Okay, so you will see this very soon, but the reason that it's called ANOVA is that asymptotically, if sample size goes to infinity, these tests are all the same thing basically, right? They don't have any important differences. Okay, so again, I'm going to start with a data set that involves just two conditions, subject and object relatives. I like these kinds of designs because they have the simplest possible setup, and you can concentrate your mind on understanding the important details in this simple case. Once you understand the simple cases, all the complicated cases are just more of the same. It's not really very interesting to look at there's not much more work involved in those things. Okay, so what we have here is some Chinese relative class data, subject and object relatives. You have a certain number of subjects, certain number of items. We got object or subject relatives. Now they have different names, right? Object extraction is an object relative, subject extraction is a subject relative. This is the position in the sentence, the word position that we are looking at. So some particular region in the sentence is interesting. These are the reading times at that critical word, which is actually called the head noun. So we have extracted the relevant data here. So one thing I've done here is, as you can see, I've used the if-else command to recode the condition levels in a sum contrast coding. So like my subject relatives are coded as -1, object relatives as +1, right? Okay, so now I'm going to go ahead and fit a varying intercepts linear mixed model with this +-1 coding for the cond column, and I'm just using raw reading times here, okay, as to get started. So I fit this model, I'm saving it as an M0 model M0, and when I look at the output, I get what I get is quite what I would expect, right? So I've got 40 subjects here, and I've got two sources of variance, the sigma, the residual variance, and the intercept adjustment sigma u0 by subjects, right? So that's the output of this model, and then there's the fixed effects and so on, right? So now I can now elaborate on this model and add one more term, one more variance component, which is the by subject adjustments to the slope. Notice the double bars mean that I'm assuming no correlation between the intercepts and slopes, right? The varying intercepts and varying slopes. When I fit this model, I get this weird complaint from Elmer, which is telling me that I have a singularity, right? So what this is actually telling me is that the variance covariance matrix cannot be inverted, right? So that's the problem here. But I mean, for now, I'm just gonna ignore this, right? When you in reality, like in real data analysis, if you get this kind of warning message, then what that means is that you shouldn't be trying to fit a complex model like the one you're trying to do. So a simpler model like this might be the best you can do, you know, under the circumstances. Another possibility for circumventing this warning message is to try to choose a different optimizer and to change some of the optimizer settings such that you can get the estimates of the variance components to come out such that they are not they don't lead to a singularity, right? All these are tricks you can try. You can actually Google all this, how to deal with convergence and these singularity warnings. What I advise you to do at some point as a fun exercise would be to fit this model, just fit this model, and once you get this warning message, just paste it into Google and see what happens, and see what kind of comments you get and what kind of solutions are proposed. Okay, so that's a good exercise. But anyway, the reason that you're getting that singularity warning is that one of the variance components, the standard deviation associated with the adjustment to the slope, is being estimated at 0, right? So that's causing that singularity warning. That's what's making the matrix not invertible. So basically what has actually happened here is that the model is having difficulty estimating this parameter. It can't be, I mean, it's very unlikely that the actual variance component is actually 0. So this is not an accurate estimate. It's just a failure to estimate the parameter. Okay, I will show you some other ways to get around this problem, right? So but let's just keep going. You could do something even wilder and fit a model with varying intercepts and slopes with a correlation between the intercepts and slopes. So you remember that the intercept adjustments by subject and the slope adjustments by subject can be assumed to come from a multivariate normal with 2 dimensions, and so we could assume that the two have means 0. That's what the model is assuming in this syntax, right? And the model assumes that there is some variance covariance matrix. I just showed this to you in the first part of this lecture, where the diagonals give you the variances for the two random variables u0 and u1, and the off diagonals give you the covariance, of the 2 random variables. The covariance is defined like this. This is a symmetric matrix, so I get the same numbers on the off diagonals. Right, so this is basically the underlying model that this this code is giving you, and again you get the singularity warning, blah blah blah. And the reason for the singularity warning this time is this -1 correlation. So as I mentioned earlier, if you get a +1 -1 correlation between the intercepts and slopes, what that does is that it makes the matrix, the variance covariance matrix, not invertible. That is bad news for us because we generally need to invert the matrix in order to estimate the parameters, etc. Okay, so but now we will look into how to get rid of these warnings, right? But as I mentioned, one exercise for you guys is to go and Google it and find out what some possible solutions might be. Okay. All right, so the model that I've been fitting, the M0 model with varying intercepts only, I can extract the residuals of that model to see what they look like. I'm checking the model assumption that the model assumption was that the residuals epsilon come from a normal distribution with mean 0 and some standard deviation sigma, right? So as I can see here, the residuals do not look very normal to me, right? So this is not a normal distribution. There's a huge skew in this direction, right? So the assumption of normality is violated. This is very bad news for hypothesis testing. For estimation, if you just want to estimate the parameters, the intercept and slope, you can get away with ignoring the normality assumption. But if you're going to do hypothesis testing on the the effect of the relative clause, you better worry about the normality assumption, because the hypothesis test actually depends on the normality assumption being approximately met, right? You will often hear people telling you that the normality assumption doesn't matter. I have said this before, but just ignore them. They don't know what they're talking about. Okay, so we are just going to stick with the standard statistical methodology. We're going to do this correctly and try to check that the model assumptions are met, and try to fit a model that makes reasonable sense. Okay, so as I mentioned earlier, one way to reduce the non-normality of the Residuals is to take the log transform, and so that's what I've done in these models now. So now I've fit 3 models on the log scale, and the 3 models that I fit are the standard 3 versions that I've taught you so far, right? The varying intercepts model, that's M0. Then the varying intercepts and slopes model with no correlation assumed between the intercepts and slopes for subject. And the third model is the varying intercepts and slopes model with correlation assumed. Okay, so these are 3 models that I have fit, and now I can try to figure out which of these 3 models I might want to use. Okay, so really the question for me now is which random effect structure, which of these 3 random effect structures can I choose, or should I choose as the underlying structure of this model. So first of all, I wanted to notice that the normality assumption is not perfectly satisfied here because there's still this annoying skew here, but it's certainly better than what we had done earlier. Okay, so sorry, this is not a very good picture here, so I wanted to show something like this, right? So we have improved on that. If we worked a little bit harder, we could do better. Maybe we could take a reciprocal transform 1 over RT or something, and might get better fits to the data, you know. So I haven't really discussed reciprocal transform, but there are many different ways of doing this, right? But the log transform is good enough for now. Okay, it's a reasonable way to proceed in this particular example. So what I want to do now is I want to act like a regular psycholinguist and just fit my data without regard to the violations of the normality assumption. And I'm just going to fit my 3 original models on the raw reading time scale, the varying intercepts model, the varying intercepts and slopes model without correlation, the varying intercepts and slopes model with correlation on the raw millisecond scale, and I'm going to try to decide which model is best. Okay, so I want to warn you that in most published work you will find these kinds of models published on the raw reading times. People never check the normality assumption, but I strongly advise you to make sure that you approximate the model assumptions when you're doing hypothesis tests. Okay, all right, so there are 2 ways to proceed. You know, there's 2 schools of thought on this. The first school of thought on deciding between these 3 models, the first school of thought is by this group of researchers, Dale Barr et al. They wrote a very famous paper that advises you to always keep the model maximal. Okay, so the basic idea here is that M2 is the most complex model that you can in principle fit, so you should always try to fit that model. Okay, so that's the basic idea here. Now, one caveat that they make in the paper is that if the model doesn't converge, and by non-convergence we are talking about things like the singularity warnings, the +1 -1 correlation, all that stuff, you know. So if you get a warning or if you get indications of singularities in the variance covariance matrix, you can consider simplifying the model, but the default assumption should be to try to fit the most complex model that you can, right? And the reason that they make this suggestion is that this is the most conservative thing to do, right? So this is the most conservative model that you will fit because it incorporates all sources of possible variability in the model, right? So it's a very sensible way of proceeding, but in reality what will happen to you is that you won't be able to fit the maximal model because of all those convergence warnings and the singularities and all that I'm showing you, right? Okay, so now the way that you're going to, so the other school of thought, okay, so this is one school of thought. The other school of thought is to try to fit the most parsimonious model, the simplest possible model, or the model that is as complex as it needs to be, but no more than that. So that's what you might call a parsimonious mixed model. Okay, so the how would you do that? Basically what we're going to do is we're going to use the likelihood ratio test to compare, for example, M0 with M1 and M1 with M2, right? So we're just going to look at the difference in the log likelihoods, just like I had shown you earlier in the lecture on the matrix formulation of the linear model. And then we will then decide based on the chi-square distribution whether to choose the simpler model or the more complex model. Okay. Now there are some technical details about how this model comparison is to be done. You have to set a value called REML in the linear mixed model to false, but even if you forget to do that, Elmer will do this automatically for you when you do the likelihood ratio test comparisons using the ANOVA function. Okay, so here we go. We've got the M0 model, that's the varying intercepts model. I've set RAML equal to false. As I said, you should set it to false when you're doing these model comparison things. So what I've done is I fit the model M0, then I extracted the log likelihood. If you remember the likelihood ratio test, I've extracted the log likelihood for this model from this model, and that number is minus 4720.2. Okay, so I do the same thing with the more complex model, the varying intercepts and slopes model with no correlation. I extract the log likelihood for that, and notice here that the log likelihoods of the two models are exactly the same. That means that I got no improvement in model fit by adding the variance component for the slope adjustments. This shouldn't be very surprising because the estimate that I got for the slope standard deviation was 0, right? So, and notice that the degrees of freedom in these two log likelihoods are different. There's one extra parameter, that's the variance component for the slope adjustment. That's why I have 5 here and 4 there, right? Okay, so now you can see that there's no difference in the log likelihoods when I do the model comparisons. So and as I mentioned some time back, that when I have a difference of 1 degree of freedom between the two models, there's only one extra parameter. This follows a chi-square distribution with 1 degree of freedom, and that distribution looks something like this. And the critical cutoff point is 3.85 in the chi-square distribution. So what I want to know is whether minus 2 times the difference in log likelihood, right? Whether that the two log likelihoods, whether that difference is bigger than 3.85 or not, right? That's what I'm going to try to find out. Obviously we know that the difference is 0, right? We just looked at the log likelihoods. The two log likelihoods are 0, so the difference is going to be 0. Therefore we're not going to be able to reject the null hypothesis that there's no difference between the models. So we would go with the simpler model in that case, right? That means the model M0, which is the model with only varying intercepts. Okay. Right, so that was just the likelihood ratio test that I talked about some lectures ago, and this I've just visualized the chi-square distribution for you guys. This is 3.85 here, right? And this is my rejection point. So if my minus 2 times the difference in the log likelihoods would have to be bigger than 3.85 for me to reject the null hypothesis. And I want to remind you that the minus 2 times the log likelihood for the there will be 2 log likelihoods for the null model and for the alternative model, right? So whether you use a negation sign here or not depends on whether you've got the log likelihood first, log likelihood of model 1 first, and subtract from that the log likelihood of 0 or not, right? So you remember I explained that which subtraction you do will determine whether you use a negative sign or not. The result of this calculation has to be something positive, some positive number. That's because we're comparing it with the chi-square distribution, which can only have positive values. Okay, so if you end up with you accidentally do the have a negative sign and then you do the wrong subtraction and you end up with a log likelihood difference of -5 or something, you know that you messed up the differences. Now luckily you don't have to do this by hand. I'm just doing it by hand once to show you how the underlying machinery works, but the ANOVA function will do everything correctly for you, right? Okay, so now I mentioned all this earlier. If the log likelihood difference is larger than the critical value, we will reject the null hypothesis that there's no difference between the two models. Otherwise we will accept that there is a difference, and then you take the, if you get a difference in the -2 times difference in log likelihoods to be larger than the critical chi-squared value, then you would conclude that the more complex model is actually the better one, and you would adopt that, right? So there's a discussion about this in a paper that we wrote once, which talks about model comparison in this way. So this way of model comparison is different from the way that Barr et al. Proceed. So Barr et al. Do not advocate any model comparison. They want you to fit the maximally complex model that you can possibly fit without getting an error message. This approach that I'm describing, the likelihood ratio test approach, is fitting the most parsimonious model that you can fit. Okay, so there are two different philosophies on this. You're probably wondering what method I use. I actually don't use the frequentist linear mixed model in my research. I only teach it. Okay, so for me it's not an issue. I work with Bayesian models always, so I don't really care about this topic much. But you should be aware that there are two different schools of thought, and you can decide which way to proceed. Now, there's actually one very good argument for following the Barr et al. Procedure. There's a very strong argument for following their advice, and the reason and the argument is that if you fit these overly simple models like the varying intercepts models or something like that, what will happen is that you will get an inflation in the type 1 error. That is very bad news, right? Because if you get a significant result with a varying intercepts model and you publish that result, you may have gotten a significant result that is not going to hold up under closer scrutiny, like if you try to replicate the result or something. So that's a very strong argument for trying to fit the more complex models. The main problem you'll encounter in these frequentist models with Elmer is that you will have difficulty fitting the maximal model, right? But we will do exercises once we simulate data. We'll be doing exercises on fitting maximal and non-maximal models, and you will understand the problem with ignoring the Barr et al. Advice, right? So the Barr et al. Paper is actually correct in saying that you should almost never fit a model with only varying intercepts. I think this is probably a bad idea, right? So the varying slopes are generally needed, to get a conservative, realistic estimate of the effect. So I'm being deliberately vague here, but I will become more concrete when I give you some exercises with simulations with linear mixed models. Okay, but all you need to remember right now is that there are two different ways to decide on which model to use: the Barr et al. Method or this parsimonious mixed models method. Okay, so in practice, as I said, I'm not going to use the log likelihood calculations by hand every time, right? So we're going to use the built-in ANOVA function for comparing models. And what this ANOVA function is doing is just comparing the log likelihoods and taking -2 times the difference in log likelihoods to compute the chi-squared statistic, which happens to be 0, of course, here, right? So we are unable to reject this simpler model. We're going to stay with that model then, right? Okay, so similarly, if we compare models 1 and 2, surprisingly what we find is that model 2 is actually better than model 1. So here in this situation, I would want to adopt model 2. Okay, so, and if I compare model 0 and model 2, I get evidence in favor of model 2. Now model 2 is the model with intercepts and slopes for subjects and a correlation assumed. Okay, so that's the most complex model here, and you can see that there are 2 extra parameters in model 2 compared to model 0. That's why the degrees of freedom in the chi-squared distribution is 2, right? Okay, so under this likelihood ratio test, using raw reading times, okay, under this likelihood ratio test, M2 is the best model. And in fact, so what we are seeing here is the situation just happens to turn out like that Barr et al.'s methodology would give us the same conclusion as we get from the parsimonious mixed model approach. Okay, so now the interesting thing is, if I were to do the data analysis in a statistically more defensible way, okay, so for me, analyzing data on the raw millisecond scale is total madness. because the residuals assumption, normality assumption of the residuals is not met, right? So for me, it's completely insanity, but I did it anyway just to show you what will happen. Now, if you do the same analysis on the log scale, I'm going to compare model M0 with M1. When I compare these two models, I again see that there is no important difference that I can see between the simpler and the more complex models. So the M0 model is the one I would stay with if I do an M0 M1 comparison. If I compare M1 with M2, I again see no evidence for the more complex model, right? And finally, if I compare M0 and M2, I again see no difference between the two models. This is a very different situation than when I was looking at the raw reading times. Now, so you should be very confused at this point, because the conclusion from the log reading time model comparisons is that M0 is good enough, right? So on the raw scale, M2 was the best model, and on the log scale, M0 is the best model. What's going on, right? What is this mysterious difference between the two model comparisons? So what's happening is that in the raw reading times, there are a few extreme values in the data. And those few extreme values are very influential in determining the parameter estimates, and they're giving you very unrealistic estimates of those parameters, and that's misleading in the model comparisons. I would trust only the log transform data model comparisons when I'm analyzing these data sets, right? So when I publish my papers, I would publish my results based on the log reading times, not on the raw reading times. Okay. Surprisingly, this is a very contentious topic in psychology. So many psychologists, I have noticed, they get very excited about this point, and they get very upset if you log transform the data. I'm kind of speechless about this whole debate in psychology. I just can't understand what's wrong with people, why they can't just read a statistics textbook and look at the theory and figure out why they're wrong. It's a mystery to me. Okay. So what I suggest to you is just that you just follow the proper statistical methodology and try to meet the model assumptions when you're doing your hypothesis tests. Okay, you'll always be better off following the theory. Okay. All right. So right. So remember that in all the models that I had been comparing, I always had the following structure. Right? I had the intercept, then I had either had the so I always had the slope adjustments, okay, and then I had the I had the intercept adjustments, and so then I also had the slope where I may or may not have the slope adjustments, right? So this was the model that I've been talking about here, and in this model the slope was always present. The interesting question was about the random effect structure. Should I include a slope or not? That was model M1. Should I include a correlation between the intercept and slope? That was model M2, right? So we always had the slope present. So now you can ask yourself, having decided on the random effect structure of your model, right? So according to this model, the random effect structure that we have chosen is the M0 model. That is the model with varying intercepts, right? So I could decide to now check with the varying intercepts random structure. I could decide whether there is an effect of the relative clause on average or not, right? So basically what I'm now going to do is I'm going to fit two models, one with only the intercept, okay, with some intercept adjustments, and another model with intercepts. So let me just write the intercept adjustment and the slope, right? So now I'm going to compare these two nested models. If you remember the ANOVA lecture I gave long ago. Oh, I just lost a connection here. Let me just quickly try to reconnect. Sorry for all this. This is very annoying. I just lost my connection. 63935355 and 1832. So what I'm doing right now is I'm trying to connect my Windows machine to my Macintosh machine so that I can have access to both the operating systems at the same time, because I like to be able to write on my slides, and that I can only do on the Windows machine and not on the Mac, and that's why I have to connect these two systems. Okay, so all right, so I think we are back in business now. No, what is going on here? Yeah, okay, so yeah, right, here I am. So what I'm now doing is I'm going to compare models with and without the slope. It's the only thing I'm going to vary now is the presence or absence of the slope. So these are the two models. One I'm going to call the null model, and the other is the non-null model. Okay, the random effect structure is the same in both the models, right? All right, so again, we are going to use the likelihood ratio test to check the fixed effects now, whether the fixed effects is justified or not, right? So what we see here, using the ANOVA function to compare the null and the alternative model, and what I get here is there's a difference of one parameter between the two models, of course, because there's either the slope is present or not, and the difference in the log likelihoods, minus 2 times the difference in log likelihoods, has the value 5.3. Okay, so as I told you earlier, in the chi-square distribution with 1 degree of freedom, the critical point, right, is 3.82. So because 5.3 lies outside that point, that critical point, I can now reject the null hypothesis and conclude that the effect of the relative clause is significant. So that's how I would report this. Okay. So now if I were Barr et al., I would proceed as follows. I won't do any model comparison on the random effect structure. I will leave it in. Okay, so here are the models with the random effect structure in, and then all I'm changing is whether the slope is present or not, and I now do the model comparison, and what I get from this model comparison now is a chi-squared value of 4.54 with a degree of freedom 1. This again allows me to reject the null hypothesis that there's no difference, because if you remember, 3.82 or 5 or whatever it was the critical point, and we are at 4.54, which is inside the rejection region. Therefore, I would adopt this model and conclude that there is an effect of relative clause. So in this particular case, whether you go the Barr et al. Route or you go the parsimonious mixed model route and do your model comparison on the most parsimonious model, you're going to end up with basically the same conclusion. So that's good, right? You don't want to be in a situation where you have to choose between one or another methodology to publish a significant result. That would be p-value hacking, right? So, but as I mentioned, the Barr et al. Method does have the important property that it's the most conservative thing you can do, right? So you're getting a conservative answer here, and it's actually something that you should get excited about, because you got a significant results and you can publish it now, right? By the way, I have done research on this particular topic, and I'm fairly sure that this claim is false. The claim that we just made based on this data, that there's an effect of relative clause, right? I've published some papers on this, but that's a scientific question. It's not really interesting. Statistically, I think this is defensible, this conclusion that there's a difference between these two conditions under the assumptions of the models that we have set up. Okay. All right, so we are almost at the end now. So all I have shown you in this part of the lecture, is how to do the model comparison. You have several choices on how to do this. You can go the Barr et al. Route and then do your model comparison using the likelihood ratio test on the fixed effects, or you can have this two-step procedure. First, decide on your random effect structure by doing model comparison, and then check if you get a significant effect with your chosen random effect structure, right? The Barr et al. Approach has the advantage that you get the most conservative conclusion, right? The parsimonious mixed model approach has the advantage that although you pay the price of having higher type 1 error, you have a better chance of detecting the effect. Okay, so Barr et al. Would actually object to what I just said, because they would say that, well, yeah, you have higher power, but you also have a higher type 1 error, right? So you don't know what the truth is, so what you're going to do, right? So, and their point is right, and I have an answer to this point, and the answer involves simulation. So we have to wait till the end of the course to revisit this question of which model to fit, given a particular design that we have. Okay, so I will answer this question later on. The last slide on this for this lecture basically shows you how you should report your results. So now let's assume that what I have done is that, what did I do? Yeah, let's assume that I'm taking the Barr et al. Approach. Okay, so this is my favorite approach in this particular data set. I would rather fit the maximum random effect structure and then compare the presence or absence, just like Barr et al. Recommend, right? So the way I would report this result is that I would say that a linear mixed model was fit with varying intercepts and varying slopes, with or without a correlation. I mean, you can decide on that based on what happens in your data set, with some contrast coding, with subject relatives coded as -1 and object relatives as +1. So all this information has to be conveyed to the reader for them to be able to interpret the intercept and slope, and to be able to interpret the statistical test that you did, right? So in many papers you will notice that the authors don't even tell you the details of the contrast coding or any of the estimates that they got from the model, right? All they tell you is that the difference between relative clauses was significant, p less than 0.05, period, right? And then if you want to now know what were the estimates in that particular data set, too bad, you're never going to find out, right? So it's very important to provide all the information associated with every data analysis that you do. And so I would give the contrast coding, and then I would explain what the dependent variable was, whether it was log transformed or not, and then I would provide the chi-squared statistic from the likelihood ratio test from the ANOVA function and the p-value associated with that, right? And one other important thing I would do is that I would print out the model M2, the estimates from the model M2. So I don't know if I did that here. So maybe just to save space, maybe I didn't do that anywhere. I wish I had done this. So never mind. So basically what I would report, let's go back to the very end, right? So in addition to all this text that I've written down here, I would report the following. Okay, so I would do the following data analysis. So let me go to M2 log here. I'm going to just run all the code, okay, just to get to this point here. I'm going to run all the code right up to here, right? And so, whoa, I got some error messages here. Oh, that's fine. So now what I would report in the paper would be something like M2 log, the coefficients. This is the minimum information that I would report in a table: the intercept, the slope estimate, the standard error, and the t-values. All this stuff I would present in the paper. Notice that I'm not using this t-value for my hypothesis test. I'm using the likelihood ratio test for my hypothesis test here. Okay, so in general you should always use the likelihood ratio test. The reason is that the t-test in the linear mixed model is only valid if you have no missing data at all in your data set. If you have some missing data, then that t-test is not going to be the correct way to do the model comparison. The more general way to do model comparison and to extract p-values from a linear mixed model is to use this likelihood ratio test. Okay, this should be your standard methodology for doing hypothesis testing with linear mixed models. Okay, so that's it. This is the main story relating to linear mixed models. There are some mysteries still about the linear mixed model, but I will resolve them when we go through the simulation lectures and the exercises that go with them.